Great pleasure to introduce Nicolina Istrati from ONJ. She will talk about the Lie group of Vaisman manifold. Please.
Thank you for the invitation, and also thank you for all the other lectures. It's very interesting to me. So I chose to speak about a topic which is different from the other ones that were discussed, I guess, which is related to the automorphism group in LCK and Vaisman geometry. So it's more of a story maybe than main result, let's say. So maybe let me start by quickly recalling definitions and notations, right? So we have a compact complex manifold, Hermitian metric, we identify it with its fundamental form. We say it's locally conformally Kähler when it satisfies the integrability condition with respect to a closed one form called the Lie form of the metric, uniquely determined by the metric also. And also we recall that this metric is called Vaisman when this Lie form is parallel with respect to the Levi-Civita connection of the metric. And we note immediately then on compact manifolds, having Vaisman metrics immediately imply two topological obstructions. So first you have the LCK one, which is first Bethe number must be positive, but you also have the Euler characteristic must be zero because you have something non-vanishing everywhere, like a vector field or one form. But okay, this was the initial definition of Vaisman, but it's not actually the definition that people really use in concrete examples. Instead, you immediately go from the Lie form to the Lie vector field, which is the metric dual of the Lie form. So you can also define it with respect to the fundamental form. Yeah, as by this relation that evaluated on B, you get the G of the Lie form. And then you have this easy characterization, which is to say that the LCK metric is Vaisman exactly when this Lie vector field is killing, meaning its flow acts by isometries in the metric. And why it's easy, it's because in general, nabla of a vector field, when you split it into symmetric and antisymmetric part, you always have that the antisymmetric part is essentially D of the dual one form. Since our Lie form is closed, you only remain with the symmetric part here. And then being killing is exactly saying that nabla of B is antisymmetric, right? So then you get this exactly that this is zero precisely when you are killing. So in practice, actually, you determine the Lie vector field and try to see if it acts by isometries or not, and that's how you know your Vaisman. But another important thing is that once you are on a Vaisman manifold, so now everything will be Vaisman most of the times. Once it means you have one symmetry, but in fact you have two. So both the Lie vector field and G of the Lie vector field are not only killing, but also real holomorphic, both of them. And so this gives you, in fact, something that I call the Lie group with two E's, which is a complex one-dimensional Lie group living in the group of symmetries, so group of both biholomorphisms and isometries of the Vaisman metric. And this is the main player in this talk. So we can already see two things. One of them is that since the Lie vector field is parallel, it never vanishes. So this means this complex Lie group acts locally freely, but it might be non-compact. And in fact, you would like to take the quotient of X by this group, of course. And in fact, you can do this exactly when this Lie group is compact. Otherwise, it does not act properly. When it is compact, you call also the manifold quasi-regular, as we have already seen. And then you have a general characterization of the quasi-regular Vaisman manifolds, which is essentially saying that they are principal G orbibundles over projective orbifolds, which have the property of having positive characteristic class. So here, positive characteristic class is maybe ambiguous because normally the characteristic class of a principal bundle takes values in the Lie algebra of the Lie group. So this positive here means there is one specific real direction, this Lie algebra, where the characteristic class takes values, and there it can be represented by Kähler. This also works the other way around, meaning if you just start from a principal positive G bundle over an orbifold, you can use that to construct the Vaisman metric on the total space of the principal one. And whether or not X is smooth or orbifold doesn't matter really. You can still construct this Vaisman metric and could, in fact, also study Vaisman orbifolds. And it is because of this positivity thing, in fact, you can go from studying principal bundles to studying ample line bundles, which are easier to study. So in fact, you might need to take a finite quotient, but up to finite quotients, all such Vaisman manifolds or positive principal bundles appear from a line bundle on the orbifold, for which then the first term class is exactly a lift of the principal characteristic class. You take one of these line bundles, you take its dual, you take out the zero section, you pick a lambda so that the Lie group is exactly isomorphic to C star over this lambda. You active that lambda on the total space of L, and then this is how you get your Vaisman manifold as a complex manifold. And if you also want a Vaisman metric, but not all will be of this type. But if you want one, then you can do this by picking a Hermitian structure on the line bundle, and then a Hermitian one which has positive Chern curvature, and then use that one to define with this formula Vaisman. Okay, so what can you do when this Lie group is not compact? Well, many things still are good, so many properties somehow are preserved. The main one is that you could still take local transversals and ask if those are scalar. I mean, projectivity does not make sense as a local thing, but linearity, yes. And indeed, the local transversals are still scalar, and this in a compatible way, meaning there is a global transversal scalar form on the Vaisman manifold, which always comes from local quotients of your manifold by this Lie. So this is one thing you can do, which is means you just study basic or transversal things without having an actual quotient. And something else you can do is to take the closure of your Lie group. So why you can do this? Because as we said, the Lie group also is a group of isometries. So it lives in a compact group if the manifold is compact. So then the closure of this will be a compact but now real Lie group. G is abelian because it's just one-dimensional complex. So then the closure will also be abelian, so it's just a real compact torus. And you can study this. And it turns out that, in fact, first of all, this Lie group and even the direction of the Lie vector field don't depend on the metric, only depend on the complex structure. And having such groups on the manifold, in fact, characterizes the fact of being Vaisman. So more precisely, I proved during my PhD thesis that when you just start from a compact complex manifold and you just look at its biholomorphism group and you see that inside there you have a compact real group which contains a complex Lie group, then for sure your manifold admits a Vaisman metric, and that complex group must be the Lie group of the Vaisman metric. So in particular, also this gives you obstructions on the dimension of this complex group that appears there. This also gives you then obstructions to the existence of LCK metrics, because this means you cannot have, for instance, manifolds with very big compact complex subgroups inside of it. You would not have LCK metrics there. So let me say a few words about the proof of this. So what do you do? Well, first of all, you have this G inside of H. H is compact. So you can, it's compact and acts by biholomorphisms. This means you can just average an LCK metric over it and suppose it's invariant. In particular, the Lie form is also invariant to the H, to this respect to this group. You pick a complex direction instead of your Lie algebra because by hypothesis such a direction exists. And since your Lie form is invariant, it must be constant when you evaluate on it. And now the point is to say, okay, but it cannot be zero on the full complex direction. And this is mainly why, because you can look on the universal cover or on the minimal cover if you wish, and study the Keller metric there. And you see that, okay, since your LCK metric is strict, your Kähler metric is not preserved by the group. But at the same time, if ever this complex direction would be in the kernel of theta, this means that the primitive of the leaf form would be invariant with respect to this complex direction. So in particular, the Kähler metric would also be invariant. And this cannot be because on the one hand, you would have that the norm is something that is constant, but on the other hand, the D group would have to act by strict homothetism. Right? So this means that indeed, at least one of these vector fields C or GC is not in the kernel of theta, and then you can make a change of coordinates and assume, okay, on one of them theta is 1, on the other one it's 0. So once you do this, then you renormalize your RCK metric. You know now that this vector field never vanishes, right? Because it's on 1 on some form. You can divide by this positive function, and you get a new RCK metric, which is conformally initial 1 and has norm 1 of some vector field. And then you use just direct computations like Cartan formula to deduce that this vector field is the Lie vector field of the new metric. In particular, it is an isometry, so the metric must be Vaisman. And on the way, we also showed that this C, this vector in the complex direction, was the Lie vector field. So there are no more complex direction in this torus that you could find. Okay, so let me just go very fast on some examples and see what's up with the Lie group there. So of course we have already seen this. So you have the Hopf surfaces which are defined by quotient by a contraction of C2 minus 0, which are topologically product to the circle and a free sphere. And you have multiple classes where then the Lie group will depend on that. So first of all, you have one is this Hopf manifold regular. So the regular means the Lie group is compact and moreover acts freely, not only locally freely. Well, this is precisely when the two eigenvalues are equal. And in this case, you also can explicitly write down the Vaisman metric, which is just a flat metric divided by the norm square. And the quotient is CP1. Then you have the next case, best case, let's say, which is the so-called quasi-regular one, where you no longer act with the same complex number, but with some weights. Yeah, then the quotient would be the weighted projective space, but the Lie group is still a compact. However, this is of course not the generic situation. So let's say the generic diagonal map will just act with two different complex numbers with mother smaller than 1, so you get a contraction. And in this generic case, so if you're not in the second one, the Lie group is just C. It's completely uncompact, not even C star. And here you can identify even explicitly the action and see it never closes unless you have some rationality condition on the lambda and the mu. But all these three classes, they are all still Vaisman, although the metric you can no longer write it explicitly. And you in fact even have a fourth class where you have a contraction which is not diagonal at all, and there you don't have a Vaisman metric. And of course, we cannot discuss about the Lie group, because as we said, such Lie group does not exist. In general, in any dimension, let me just say what's the story about metrics, because we already heard about this in fact. So first of all, a Hopf manifold in general, sometimes also called maybe primary Hopf, is defined as the quotient by any holomorphic contraction of Cn minus 0. And then we know that such manifolds, by work of Godushano, Verbitsky, and also you can deduce this from the proof of Brunella, is that such manifolds always admit LCK matrix. So the first results, they give implicit matrix, but over which you have more control, so you can also see if they are sometimes Vaisman. While Brunella's proof just gives you some LCK metric, but you don't even know if it has potential. It's like a very general construction which does not use the specific form of that control. You can also ask when are these Vaisman, and then so Godushano is always in dimension complex dimension 2. But these ideas are basically the same, which then are generated to any dimension. Which is, so the result is the following: when gamma in some coordinates of Cn can be put in diagonal form, then such a Hopf manifold is Vaisman. And in the other one, in the other case, so when gamma cannot be put in diagonal form, well, I mean, here, the result is that in that case, you cannot have Weismann matrix. So I think, Liv, you talked about the linear case, and I think you also told me you can probably deduce the general case from the linear case, but together with Alexandra, we also gave a different proof of this, which I will describe a little bit, but which is really given by studying the automorphism group of the Hopf manifold and seeing that you cannot have Lie groups there. Yeah, so let me just sketch the proof of this. So the proof being is Weismann if and only if gamma is diagonal. And as I said, study the structure of this group and see when do you have a Lie group. And this was exactly also the idea of Belgun, who proved this in dimension 2. But in order to study this, now we use the so-called Poincare-Dulac normal form, which tells you that you can put this contraction in a specific form where you have the diagonal part, and then you need to add some special polynomials, but which are polynomials, not just any analytic maps, and which only have specific monomers, which are called resonant monomers, and which come from the special relations that the eigenvalues of the zero of gamma satisfy. So I will not go into that because I will not use that, but it is important in general for the theory. And then this is exactly what you use. Okay, so in general, let's say if you are already diagonal, you don't care, of course, there are no GIs. If you are already diagonal, you can easily identify one complex group which sits in a compact group somewhere. And this complex group is exactly given by, you need to take the modules of the lambda i's and exponentiate those. And then you complexify this group, and you can easily show that this lives in the standard torus modulo lambda, and it has compact closure. And so if in some other way you know that your Hopf manifold is already LCK, then this Lie group automatically implies also that you have some Weismann metric on that manifold without actually necessarily writing it down this metric. What about the other case? Well, the other case, you need to know more about the automorphism group. And then this description was given by Hefliger, which showed that in the general case where gamma is possibly non-diagonal, you can still compare the automorphism group to the automorphism group of the case when the manifold would be diagonal. So in fact, this automorphism group can be seen as the centralizer of gamma inside of the automorphism groups of lambda. And then instead of actually studying the centralizer of gamma, which would be hard in any dimension, or in any case, you would need to make many specific computations, we study directly the automorphism of X lambda, so the case where you would be diagonal, where there it's easier because you have a specific structure which you can identify. You can write down exactly what are the generators. And you have, in fact, this Lie algebra is a semi-direct product of a nilpotent complex Lie algebra and reductive Lie algebra, which is a subalgebra of the linear maps on CN. Then you look closer and you exponentiate this, but on CN, so it's easier to work on CN than on the compact quotient. And again, the G reductive is just linear maps. While N, you can look at each vector field and compose them in all the ways and see rather easily that N will be simply connected. So in particular, biholomorphic to CK, there is absolutely no direction which closes up. So you don't have compact tori, let's say, instead of. And so your, let's say, automorphisms of Cn, which commute with diagonal action of lambda, sits in an exact sequence of nilpotent complex Lie group and then a reductive group. And this reductive group also can be seen as a subgroup of the initial big group. So then if you have some Lie group sitting in some H, you study it with respect to this exact sequence. So what you first do is you're going to have to lift it on Cn, and then you will see and show immediately that while G might lift on Cn, H will not lift itself. Instead, the Lie algebra will lift, but then when you exponentiate it, you will see that it exponentiates to a cover of H, which in fact contains your contraction gamma. Yeah, so it's in fact the Z cover of the compact group. So now you look at this one, as I said, the nilpotent one group has no compact direction, and because of this, and you will show that it cannot intersect the lift of H. Even if H is not compact, it's almost compact because it only has one non-compact direction, and it also has this complex direction. So because of this, you can deduce that it does not intersect. And so this means that basically your lift of the torus is isomorphic to the one which sits in the reductive group. There, you know what normal compact tori look like. Then you know that they are conjugated to the standard one, diagonal one. And using this, somehow you identify what Q of H can look like. Also knowing the fact that it contains Q of your contraction gamma. Yeah, so studying this in the reductive part, you can show that this lift of the torus must sit in the standard torus sister to the n. So going back, this means that your contraction is already a diagonal map times maybe something nilpotent from n. So you don't yet know that there's no nilpotent part, but in any case, you know what happens to the reductive part. Okay, now finally, now you're here, you know that, so your H was commuting with gamma, with lambda. So because of this, now you also know it must commute with gamma n, with its nilpotent part. And this allows you to define a well-defined map from the Lie group to this nilpotent group intersected with the centralizer of gamma n, modulo gamma n. So what you're doing here, when you intersect with the normalizer, you're still a closed complex nilpotent Lie group. Gamma n is the discrete here. So what you get holomorphically is something like C star times, so C star times CK. Yeah, so you're getting a holomorphic map from G here, which must be bounded because in fact it comes from H, which is bounded. And this holomorphic map by Liouville must thus be constant. But what does this holomorphic map do? It exactly detects what are the nilpotent parts in your Lie group. Yeah, so it kind of projects in a not as a homomorphism, but just in an holomorphic way. It projects T to the nilpotent part. So since this is constant, this means simply that your Lie group and also this H group were already in the reductive part. So in particular, your construction is just diagonal. Okay, so this is really just a study, a careful study of the automorphism groups and different properties of nilpotence and reductiveness. Okay. So let me then just make this general remark that in what happens then in if you only look, so we said not all Hopf manifolds are Vaisman, then let's just look at those which are Vaisman. So they are all diagonal. So you can put them in a very nice family, which are just parameterized by this lambda 1, lambda n, right? So it's just complex numbers which sit in the unit disk, minus 0. And you can see from these different properties, I mean, it's rather easy to see that you can detect the Lie group. I already wrote it down a few times ago, a few slides ago. So by identifying this Lie group, you can see exactly when it's compact, and you see it's compact exactly when this these complex numbers by which you act, they all come from one acting with different weights. Yeah, so this means basically that the generic Hopf diagonal is not quasi-regular. However, you have many which are quasi-regular and they are dense in this family. And so already looking at this most important family of Vaisman manifolds, you see two aspects. One of them is you can easily deform a little bit quasi-regular Vaisman manifold and get a completely non-regular one. And as was seen in dimension 2, but it's true in any dimension, you can easily deform a diagonal one to a non-diagonal one and then go from Vaisman to non-Vaisman. Yeah? So you're unstable both to being quasi-regular, even if you only stay in Vaisman deformations, and also unstable for compactness of the group. So then the question is, do we even have sometimes some conditions which imply regularity or stability for this sort of properties? And the answer is yes. You sometimes have such a you have such a condition, which is somehow the easiest one, is to ask that your manifold is rigid in some sense. So meaning it has as few automorphisms as it can, so only one-dimensional complex automorphisms. Yeah? So in other words, you ask that you start from a complex manifold whose automorphism group is only the Lie group. Then the statement is that if you start from such a manifold, every time you make a small deformation of it, you are necessarily both Weisman and also quasi-regular. And you can also ask, okay, but do you even have such manifolds? And you do, and this even can be ensured by cohomological or analytical numerical invariants. So you can make explicit examples of these numbers. So if you know, for instance, that the first term class in the RAM cohomology is 0 and the code area dimension is non-negative, then we can show, and I will just say 2 words about this, you can show that in this case, you have very few automorphisms. So what are the 2 words about this? Now, maybe first one remark. For the Hopfs, there is no 2 homology group. So the first chunk class does vanish, but the code area dimension is negative because in fact they are toric, so they're kind of the opposite side. Yeah? So they don't satisfy the second numerical condition, which you do need if you want this. And then just a few words about the proofs. Well, as I said, this condition means that the identity component is G. So this means if you try to take the closure of G, you're gonna just be the same because there's nowhere where to go in this automorphism group. So this means G is already compact. And then you can show that in general, if you have a complex manifold for which the automorphism group is compact, and a small deformation of the complex manifold induces small deformation of the automorphism group of the manifold. So in particular, if you start from a compact automorphism group, you also get a compact automorphism group. Now you use 2 things. So on the one hand, you know the automorphism group is compact. On the other hand, you use the result of Levy and Misha, which says that when you deform a Weisman, you are actually deforming an LCK with potential. So you are maybe not Weisman, but you are still LCK because you're LCK with potential in particular. And so then you apply again this result that I told you about from the beginning, which is, you know your LCK, but you also know that the automorphism group is compact complex. So this means in particular that there is a Lie group inside of it. So therefore it must be Weisman and then also quasi-regular. And the second condition, in fact, goes through the existence of special canonical metrics, which are essentially transverse Keller-Einstein metrics. As the first term class vanishes, essentially means that the first bond term class can be represented by a transverse scalar matter or minus of it, or it's just 0. So you have in fact 3 cases there. In the negative dimension, it's hard and you don't know what to say. But in the non-negative code area dimension, you can show that there is, once you fix some cohomological data, there are unique canonical metrics, and then you can either use the existence of this unique canonical metrics or some Weizenburg techniques to show that basically any biholomorphism of your manifold is already the Lie vector field of some multiple of it. Okay, so let me maybe
Sorry,
just
Nico,
finish.
sorry, just a moment.
Yeah.
So you have what you're saying is that in this case you have transverse Keller-Einstein that is Calabi-Yau on the covering.
I am in 2 different situations. So I'm saying if
No,
first term class is
the third one, imply existence of transverse Keller metrics.
it's not Calabi-Yau
Keller-Einstein.
on the cover. No, it's
Yeah,
not
it's
Calabi-Yau on the
Calabi-Yau
cover.
on the cover, yeah?
No, it's not Calabi-Yau on the cover.
It's not?
No, it's not. It's Calabi-Yau on the base, but not on the cover. So to be Calabi-Yau on the cover is exactly the code area dimension being negative. It's the hard case.
Sure.
Yep. Yes. Yeah. So example where so first chunk class is 0 and both chunk class is 0.
Sasaki Einstein on the it's the same as you say.
Yeah, but I'm not. So you see, when I say transverse scalar Einstein, this doesn't imply Einstein-Weisman. This is a different sort of condition.
Einstein-Weil, not Einstein-Weisman,
Yeah.
Einstein-Weil.
Yeah, but I'm not talking about Einstein-Weil. So I'm not talking about this matrix. I'm talking about some other matrix which you can still define in a canonical way and use those to like detect different rigidity things. But these are not Einstein-Weil metrics, though. Yeah, so Einstein-Weil, just to comment with the relation of Einstein-Weil metrics, Einstein-Weil metrics would correspond to positive Keller-Einstein metrics, which are transverse. Yeah, so when the base is
so
one.
not positive, transverse scalar Einstein, which are not positive. Okay.
Exactly.
Because
Yeah.
I was thinking about positive orbifolds on
Yeah,
the
no.
closed.
So positive orbifold is exactly codaira negative. This is what I was saying.
Okay. Sorry.
Yeah, so the other codaira is in fact equivalent to negative or zero transverse scalar.
Okay, Vlad's condition. Yeah, okay, thanks. Sorry.
Yeah. Okay, so let me then just I guess it was a bit fast, but yeah. Just comment on what you can do in general. Okay, so you cannot, you don't have, I mean, sometimes you can have G compact and then you're happy, but if you are not, what can you do? I mean, and then what is happening is that, like in the Hopf case where you could put all your Weismann manifolds in a nice family and then detect which one are quasi-regular and which are not, you can do this, in fact, with all Weismann manifolds. On what and which way? So for simplicity here, I assume that my Weismann metric is rank 1, but you can in fact do this with any Weismann metric. So I start with compact Weismann metric, rank 1. I take its Lie group. Let's say it's not compact. I take its closure. This gives me a compact fair torus. Then I don't look at this torus because this is not necessarily so good. I'm gonna take its intersection with the maps which act in a Hamiltonian way with respect to omega. So there are in fact multiple ways to define this torus. This is one of them. The point being that this allows me to define a codimension 1 subtorus, so closed subtorus of H. So it will, you can write it as it's Lie algebra with respect on a lattice. And why did I take this Hamiltonian part? Because I want something that is purely real. So purely real means it has no complex direction inside of it. H will have a complex direction, which is the Lie direction. And basically doing intersecting with Hamiltonians allows me to just kill this complex direction. Okay. So I have this Lie algebra. This means then that it is in direct sum with G of it, so there is no intersection. And I don't look at all vector fields there, but only at those vector fields on which my Lie form is positive. So this will give me some function. I ask it to be strictly positive everywhere. So this is an open subset in the complexified Lie algebra, which is just the CK, where K is the complex dimension of this complex, or the real dimension of the real torus, if you want. So it's at least 1. It's exactly 1 when G is compact. And then this is basically the result, which is a formulation of different results existing in literature, both in Sasakian and in Vaisman, but formulated in terms of existing of a family. So I also said Gudush because there is the first time I saw this idea of constructing Weismann metrics starting from a given explicit Weismann metric, but then different sort of ideas appeared everywhere. So what is the statement? The statement is then that this open subset of the complexified torus parameterizes a family of Weismann manifolds, but not just of Weismann type manifolds, but you can in fact define a metric on the full total space, which is not metric, it's a form which is restricted to each fiber is a Weismann metric. So it's a form which varies smoothly with respect to the base. Your given starting Weismann manifold is a fiber of this family for some of them. And then since you are using this torus, you can, why did we in fact use this torus? Because this allows you to see what happens with the Lie group when you do this. So what you are doing here, you're gonna deform in the complex structure of the initial Weismann manifold in a way that this deforms basically the Lie direction of the Lie vector field. And you can do this in a controlled way, meaning over each psi, you can decompose each of these psis in the torus part and G of the torus part. And G of the torus part is exactly the Lie vector field of this Weismann matrix. So you can detect exactly from this psi the Lie direction. So in particular, you can detect the Lie direction, and you can also say when then is one of these fibers quasi-regular. And this is exactly when this G of psi of t is rational with respect to the lattice that you have. And the torus part this is a bit weaker condition. It's also rational, but maybe not rational, but rational up to the direction of the Lie vector field. So basically, the first condition is equivalent to saying that the associated Sasaki is quasi-regular, but this is weaker. And the second one also makes sure that the fully grouped closes and not just one direction. Okay, so this is basically the statement. And also here the sentence is that quasi-regularity is a rationality condition. Therefore, in this family already, rational things are dense, even if everybody is not quasi-regular. So I will just recall and describe the construction, as I said, in the rank 1 case. So why in the rank 1? Because what do you do? In the rank 1, rank 1 essentially exactly means the fact that you have a Z cover of your manifold where the Lie form becomes exact. So you're going to use that one to construct the family. So what is the family? The family is you're going to take just the product of this minimal cover with this open subset. You're going to construct a Z action on this product, which is compatible with the projection to U+. And you're going to construct a smooth function on this product, which, when using the correct formula for the Vaisman matrix, so using the fact that it's a metric with potential, if you're going to derive only in the direction of x, you're going to get this relative Vaisman metric. Yeah? So you need to construct this function to make sure that it gives you a positive function and so on, a positive metric, and so on. Okay, so this is the point and this is the goal. So in particular, this deformation that you make in this way, they don't deform the minimal cover. They only deform the action of gamma on the minimal cover. And so the deformations are only induced in this way. And so, as I said, H, so this initial H, you cannot lift it on the universal cover, just like in the Vaisman, just like on the Hopf manifolds. But what you can do is lift its Lie algebra and then exponentiate it there, and then see that this must be a Z cover. So this is already an argument that is sold in the book of Livio and Misha. You notice that this must be a Z cover, and therefore this Z cover must be, it's like the cover is by finite index subgroup of this gamma. Maybe it's not the full gamma, but we're going to suppose that this L is equal to 1. You can, just to make it more easy. So what does this mean? This means that this gamma thing generating the deck group sits in this torus, right? So maybe not compact, but it's not a problem. So this means it's the exponential of some vector field. And then it's the exponential of some vector field, and you can also identify directly the Lie vector field of the metric, which is exactly the GT part of it. Again, by compactness argument somehow. And then, again, this is an argument that was already used in the initial construction of Vaisman metrics on Hopf surfaces, which is, in fact, why did we take this U+? So U+ condition was theta is positive on psi. Well, this is exactly the condition that ensures you that when you look at the flow along this vector field, starting from the associated Sasaki manifold, which is exactly, so I didn't talk about Sasaki geometry, but you start from phi minus 1 of 0. This is the associated Sasaki manifold. You take these terms R, you flow along this psi in this way, so you are going into the minimal cover of their manifold. This defines the deformations of the manifold. So in other words, each of these vector field in U+ is a way to define a trivialization of your minimal cover as a principal bundle over the associated Sasaki manifold. And you are just splitting in some way the manifold as Sasaki times R. But this always depends on this psi vector. And you're going to use this vector field in order to go back somehow or to compare with your initial reference metric in order to define basically for each psi a diffeo of the manifold, not a biholomorphism, but a diffeo, which you're going to use to both define your phi psi, so your function which you want to be strictly plurisubharmonic. And you also are going to use this map to somehow switch from the initial deck group action to a new deck group action, which is by taking the flow of this psi that you started with. Okay, so what this map essentially does is it is going to topologically trivialize your family, but moving the complex structure on each like in a new way. Okay. So use this map both to construct the Vaisman relative Vaisman metric and the new deck group action. So in other words, this phi tilde is going to be given by this function in every psi. And the action is going to be at every psi given by the flow of the one-time flow of this psi. Okay, and this is how it goes. And when it's now from one, you can still do the same, but you just need to like carry over some terms. So the formulas are a bit more involved, but the same ideas kind of still work. So just to finish up, so this is still the same slide that you have seen. Just to finish up, maybe what remarks can I make here? One remark is that if ever your Lie group was already compact, this family still makes sense. U plus, as I said, will be one-dimensional. And what you're going to do in this family is exactly perform deformations along the Lie group. You're going to still deform your complex manifold, but in a way which only induces deformations on the Lie group. Yeah, so you just you have the same base but different Lie groups, different structure and the same elliptic curve. In general, what it does is that the Lie group, as I said, will just stay inside the exponential of this torus. So in this family, all the Lie groups can only be smaller or as big as the initial manifold. Now, this is the only thing that you do. You cannot make the Lie group bigger in these deformations. You could, however, this I will not talk about, but you could in principle make a larger class of deformation. And there you could also make the Lie group bigger. But this family really depends, this construction depends on the initial Hopf, initial Vaisman manifold from which you started with, because you did fix this H group and you use that one to construct it. Okay, and then you just go smaller or the same. Okay, and I will stop here.